DeFi by Design, where we talk all things blockchain and cryptocurrency while striving to educate, empower, and enrich.
What's going on, guys? Welcome back to the DeFi by Design podcast. This is episode 98. We are here with Ismail. We're going to be talking about Lagrange Labs. Lagrange, we're going to hear more about it. I believe it's a mathematical term. I remember hearing about it throughout classes. So we're gonna talk more about that, what it is doing in the Ethereum space. And Ismail, I mean, it's good to have you on. It's good to have you on.
Thank you.
And could you introduce yourself and tell us what you do with Lagrange?
Thank you, Rob. I'm excited to be on. And you're correct. Lagrange is a French mathematician, and he's responsible for a number of the constructions that are highly important for zero knowledge proof systems. So, great to meet everyone here. I'm the founder of Lagrange Labs. We build types of cross-chain interoperability, state and storage that is more performant than messaging protocols and bridges for certain DeFi applications. The way we like to describe it is that if you deploy n instances of a DeFi app across n different chains, there are implicit relationships that exist, some of which are one-to-one, like what messaging protocols and bridges handle, and some of those are more complicated and depend on more dynamic data relationships. And those are some of the things that we built.
And the architecture you mentioned is ZK, yet the user experience, I envision when you say n app instances over n chains, sounds inherently cross-chain. So
yes,
could you explain the relationship between the ZK architecture and still the compatibility among chains?
That's a very good question. The way we like to think about cross-chain interoperability is as a fundamentally modular product. There are, in our view, three principal components. The first is state validity. So how do you prove that a given block header is in fact valid for a given chain? In traditional bridging, this is done through intermediary nodes or K-event assumptions over some protocol responsible for attesting the state. There is the second component, which is transport, which is what actually takes that block header, that proof, or that attestation of state and writes it somewhere else. And the third component is what we think of as computation. In other words, what can you prove within this block header, and what type of data schema manipulations can you do to the underlying format of the message? And when we think of cross-chain, we think of these three components as, in the final state, very independent, wherein applications can potentially grab different computation layers, different transport layers, and different validity layers in order to properly build an application that can handle whatever the application-specific requirements they have for their multi-chain dApp. And so what we focus on is twofold. We focus on building novel computational models to prove expressive computation on top of block headers. And this is one of our products that we refer to as ZK Big Data and ZK MapReduce. So how can you take a given block header and prove these arbitrarily large, for example, pricing relationships on it? Moving averages of price, TWAPs, VWAPs, etc. And the second component of what we build is what we think of as state committees or state proofs. So how do we allow for certain chains applications to prove or consume proofs of the state of that chain without requiring insecure intermediary attestations? So entirely zero knowledge.
There's a lot to unpack there. Okay. When you talk about block headers and information in blocks, before we get to what you guys do with a block, could you kind of flesh out like the components of a block with respect to how you then use this block?
That's a very good question. Yeah. So within a block header, you can think of it as having a number of properties and metadata associated with that block, as well as multiple trees that can be used to determine the state of various aspects of the chain at that point in time, or that block height. That includes the state tree, which encodes all contract state in that chain and all account state in that chain. The receipt tree, which is all execution traces, and the transaction tree, which is all the transactions included in that block. All three of those are Merkle Patricia tries and encode different aspects of the chain with respect to that certain block height. So when we think of computation that you can run on top of a block header, it's how do you leverage these existing data structures and zero knowledge computation on top of them to be able to derive relevant properties about the chain at that block height from that block header. For example, all block headers contain contract state, which means if you want to determine the price of UniV3, the spot price, for example, you would need to run a Merkle inclusion proof on 2 leaves of the tree at that height to determine, let's say, both volumes of assets in that pool. If you, for example, now want to do a moving average of that price, you would need to do multiple blocks in a proof, which could be done on multiple block headers, or it could be done on a single block header where you prove what the historical block headers were with respect to the current block header, since they're all linked. And this allows you to have these,
Can these block headers synchronize across chains? You have a block header on an Avalanche. Can you sync this block header in one Merkle tree with a block header from Arbitrum?
So someone could relay them over, but the block header is a inherent structure to every chain, and as such, they're not intrinsically linked, and that's where I think, looking at it from a meta perspective, that's where cross-chain really comes in. It is we have all these disparate data structures, which we can almost think of as independent databases, where every block is a version of that database. On top of this, we have one giant asynchronously updated data lake. What with all this information can you build? Right now, we think of cross-chain as this one-to-one relay, where you take the current state of one chain and write that to the next chain. But as we look at it from a broad perspective, and we see all these settlement layers and all these updates to these inherent data structures, what are the things you can build on top that aggregate proofs of stake?
Yeah, you've thought about this question much more than I have. How do you at Lagrange address this question?
So we build computational tooling that allows you to efficiently prove properties across all of these heterogeneously updating independent settlement layers, independent block layers, where you could have computation that you can verify that runs on top of state across a series of different chains concurrently. And the question of what you can build on that, we're unopinionated on what you should build, but there's certain use cases that we think make a lot of sense. I think most DeFi apps that we've spoken with have issues and concerns over how they're pricing collateral. Options protocols, lending protocols, derivatives protocols are all dependent on off-chain price feeds in order to price assets. And these off-chain price feeds generally don't account for liquidity of an asset pair. They don't account for how much slippage you get at the point of liquidation, and they don't account for where that liquidity is located. So if you're on Arbitrum and someone gives you $10 million of wrapped Algorand collateral, there's a question of what you could actually liquidate that for in the event of a liquidation event. And so this is why a lot of protocols struggle to support long tail collateral. As you now start being able to unpack and unfurl some of these more complicated data relationships, you can remove the dependence on these static off-chain price feeds and instead price collateral natively based on how much you could actually liquidate it for realistically on the settlement space, on the execution space where your application is deployed.
Okay. In terms of the user experience, from a user perspective, this looks like lending on Avalanche. I can collateralize my chicken NFTs on Avalanche in an NFT lending protocol, and I can take out a borrow position to buy things on Arbitrum natively, make that borrow on Arbitrum, and then when my so I would then need to repay my loan or get liquidated, in which I would need to know how. There would be a question of how much to liquidate my NFT for on Avalanche, right? So the liquidity circumstances on Avalanche would need to be, they would need to tell Arbitrum when to liquidate my position. Is this?
You see that I love this. This is what I love about this type of technology, because that's entirely different than the use case flow that I was thinking, but that's also a completely valid one. And that's actually a very good use case when you want to lock an asset on one chain and lend against it on a different chain without requiring it to move or be wrapped. And that's another very, very interesting use case. The example I was saying was just very simple, where you have one asset on Arbitrum and you want to lend that on Arbitrum, for example, and the protocol wants to know how much it sells for on just Arbitrum without worrying about any other chain's price. But the instance when you're talking about trying to price something cross-chain is another one where this type of functionality is very important, especially when you consider price to be a factor of multiple dexes concurrently. To say Arbitrum needs awareness not just of what Trader Joe is on Avalanche, but it'll need what Sushi is on Avalanche. I don't know if UniV3 has a deployment on Avalanche, but if it does, it'll need to know that too. It'll need to know where to liquidate it to. It needs to know when to liquidate it. It needs to know all these properties associated with that state of the chain. And that is where some of the more dynamic computation, more dynamic cross-chain relationships that aren't necessarily handled by bridges and messaging protocols become very relevant.
Okay, so you were describing how Lagrange interacts with the state of the chain and its block headers.
Yeah.
And I interrupted you and asked a question. So could you, now that we know like what a block header is, could you describe what Lagrange does with these block headers and these and how it could you kind of explain the block header's role in the state of the chain?
Yeah. So every new block has a new block header. And when we think about block headers in the context of cross-chain, we really need to think about kind of the logical flow of what one does with a block header. So if you have two chains, Ethereum and Avalanche, let's say, and you want to use the state of Ethereum on Avalanche, Avalanche can't make an external call to Ethereum and figure anything out. So Avalanche needs to be able to verify things just natively within its execution environment. So what does it need to verify? That some random group of bytes that correspond to a block header are in fact the correct block header at a certain height on Ethereum, right? They're not just a block header I made up, it's not just a block header you made up, that this is in fact the correct finalized canonical block header at height X. Next, it needs to verify some computation that's done on top of that block header. Unless it runs all that computation natively on chain, which is going to be expensive, you would ideally want to run that as your knowledge context to verify it succinctly. So you need to prove almost two properties in this case. What is the block header, and what am I doing on top of the block header? And so Lagrange has a few different mechanisms to handle each of those components. For chains that have a block header structure or finality of consensus that's provable, right, where you can generate a proof for the consensus of that chain, we generally use that because there's no reason to have anything else if you can just prove what the block header is based on how the chain executes. For chains that don't, for example, think of an optimistic rollup where finality is defined by game theory and not by a provable mechanism over a short period of time. Then we have what we call state committees, which leverage restaked or rehypothecated collateral to execute verifiable attestations to state that we can generate recursive proofs on. And once you now kind of take it for granted that you have that block header that you can prove is valid, you can run computation on that. And the computation that we most natively support is distributed computation. So highly efficient big data scale computation that can be run on top of these on-chain state structures, right? Which is anything you could run in RDD, distributed SQL, MapReduce, etc. You can now run in the zero knowledge context on top of our ZK big data framework.
Okay.
And this allows you the pricing and all these things we talked about before.
Got it. Okay. And yeah, there is some technical components that are they sound like they're very they're very abstract, but they're very advanced. Like you guys have spent a lot of time thinking about these block structures and their current mechanisms, right? Which are mostly game theory secured. Like proof of stake secures the Ethereum blockchain, obviously, and then the idea there is that the validators are proving the validity of the chain, and each time they make that proof, they post a new state of the chain. So then there's all the ZK kind of
Yeah.
computation on top of the game theoretically secure chain. Um, what's your opinion on ZK at the base layer? Do you have,
Yeah.
do you, I could kind of anticipate, but I'm curious what you think of uh, ZK Sync or the other ZK native layer ones.
Yeah, we think very highly of any chain that uses zero knowledge to prove its state transitions as a rollup on Ethereum. We also think very highly of optimistic rollups. I think they both have use cases that they're very well optimized for and very distinct advantages and disadvantages. I think that being able to prove an arbitrary state transition um, on a EVM, for example, as ZK Sync would do or as Starknet does, allows them to leverage efficiently the existing collateral that underlies Ethereum consensus in order to secure themselves. And I think this creates these very interesting structures where you can nest these rollups on top of each other and create increasing amounts of scalability and ideally atomic transactions between each of these layers that have really only an increase in settlement time rather than an increase in, for example, rather than a drop in security to try to increase block space and throughput, right? Where you can keep nesting rollups on top of each other, and all you do is increase computational cost of having to compute all these state transitions, and all you do is increase the time to fund, but you don't decrease security. And that's, I think, a very interesting property of nested ZK rollups. So we're very, very big fan of those, and we're a big fan of nested overuse too.
Got it. Okay. And Lagrange is not at the layer one level. It is the main application to create Merkle trees of various chain states.
Yeah, so we're not a layer one. So our goal is to help cross-chain interoperability be as functional and expressive as possible. So the question is, what can you do between chains? And that's the question that we're answering. And the technology that we use to answer that is entirely zero knowledge proof based. So we're not on the L1, we're not like a messaging protocol, like a layer zero and Axler, though we do work with some of these protocols to help with security and to help with expressivity of computation. We're very much, you can think of us as tooling for building dApps that are more functional and are more dynamic, right? So if you think
Is it
about
fair to
a
add?
DeFi app,
Yeah.
pardon?
Is it fair to add scalability into those other ways you describe a more useful overall app?
Yeah, I think scalability is very important. And the way we think of it is that if you are building a dApp today, you might just be able to build it with very closed, simple state transitions on one chain. But it's very likely you're going to need awareness of two things. You're going to need awareness of other applications on the chain you're on, potentially awareness of the historical state of those applications, and you're going to need awareness of the present and historical state of cross-chain applications as a developer of a DeFi app, right? Lending protocol apps need this, options apps needs this, derivatives apps need this, yield ags need this when they're routing asset allocations. Most modern DeFi apps need awareness of external applications beyond themselves. What we do is we build tooling that makes that more efficient.
And in the traditional financial world, this
Yeah.
is common. Like there's
Yeah.
multiple exchanges and there is interoperability of price feeds from multiple sources.
Exactly.
Does this occur when and you may not know the traditional financial
Mhm.
format of how they share these data feeds, but on the blockchain, no matter what traditional finance comes up with, it seems more efficient because it's almost like we're all interacting with this interoperable database. Whereas
Mhm.
I doubt traditional financial institutions are sharing databases with one another,
Mhm.
but it's not as it's not as cohesive because they're not sharing that information. So, two-part question: how does how does latency work when you're
Yeah.
sharing data from chain to chain, and how does this relate to a traditional financial
Yeah.
architecture, um, database or otherwise, where they share price feeds?
Yeah. So that's a good question, right? Because you still need to share price feeds in traditional finance, to your point. Because if you're a lending company and you allow someone to post a stock as collateral to take a loan on that, you're going to need to understand the price of that stock, the spot price, and then whatever price you can liquidate that for in the event that someone's margin, in the event that someone gets margin called. So I think that's a very important aspect of trying to build any system, right? Where if you had to liquidate a stock to a certain exchange or a certain order book in the event that someone was margin called, you would need to know the price that you could liquidate that for to understand when to make the margin call. And when you think of these kind of atomic liquidations on chain in these over collateralized lending apps, there is really no ability for them to understand a priori to a liquidation how much they could liquidate that for. They have to rely on a secondary price feed that would feed questionably accurate data back in, derived from opaque sources that they're hoping that they could liquidate for that amount, right? Like a Chainlink price feed does not accurately say how much you could liquidate ETH for on a ZK Sync L3. It's a uniform single price of what they believe Ethereum trades for everywhere. There's no context and no location for that price information and price discovery. So that creates some somewhat problematic dynamics when you think about building these DeFi apps that have to be anti-fragile and able to run atomically without user intervention. And so when we look at Web 2 movement of information, it's very simple to transact between two applications where you just call an API and they return you data in some predefined format. In Web 3, it's a lot more complicated because these chains can't call externally. So you're generally constrained. Exactly. You're generally constrained by the data you can access. And so what this type of functionality allows is for people to build more dynamic, more expressive, more anti-fragile, more secure DeFi apps by really being able to leverage these inherent data lakes that these applications sit on top of.
Okay, so the current architecture of interoperability across chains puts the state channels of one chain into this cloud-like, it's a very Web 2 term, but cloud-like structure above the chain. And then to access data from another chain, this other chain B over here would have to pull that data in from that cloud-like data sharing structure. Whereas this ZK technology could share state channels directly to the chain without a intermediary, albeit maybe decentralized one.
I think that's a very good framing. I think when you think of how we would feed multi-chain data to a chain right now, it's going to be through an oracle, right? Where you run a bunch of nodes or I run a bunch of nodes and we feed data back onto one of the chains. You can't have a chain that or an application on a chain that dictates for itself what data it wants to consume from what block height, from what formula for how they want to derive these properties and run it themselves, right? So you lose the agency as an application developer to really be able to customize how you would like to consume multi-chain data. And if you were to consume it for an off-chain price feed, you lose security, right? Because you're inherently building a trustless application with a heavy trust assumption on your data source. And that's a limitation that we have today.
Yeah,
and with cross-chain,
and Chainlink always had these. It was honestly, it's about time, that like there's a project that kind of calls out not that you're doing it specifically, but your product calls out the inherent centralization weaknesses of Oracle systems in general, like Chainlink specifically, who's always kind of been called as a relatively centralized service. In blockchains in general, decentralization is normally an advantage, and this is decentralizing Oracle services as a product in general. Is that a fair assessment?
Yeah, I think that's a very fair assessment. When we think of oracles, you always have the need to feed off-chain data that's inherently off-chain, on-chain, right? Like if I want to determine how much a square foot of real estate in Soho is priced at to issue some on-chain equivalent to that. We always need an off-chain feed. But for data feeds that don't rely on off-chain data, the use of an off-chain set of nodes to feed that data on-chain today is a limitation in infrastructure and architecture because we don't have these types of computation to allow you to do that right now. Where you can't prove, these end-to-one relationships across a series of other chains and a series of historical blocks in one proof somewhere. So you have to rely on the off-chain actor to go aggregate that data for you and tell you the result.
And this is why all of those Oracle systems are game theoretically secured, because
Exactly.
they don't they don't have the compatibility chain to chain to secure them based on a proof of
Exactly.
proving the validity of state channels on one chain, so that the other chain shares that proof.
Exactly. And then as you kind of think of the derivative of this and you start going a level deeper, one of the advantages you have is not just the security, but the expressivity. Because now that you don't have to rely on some off-chain actor to feed you data every so often, you can build applications that consume data in novel and personalized ways to that application, the same way they would if they were building data infrastructure in Web 2. And so you increase security, and by extension, you then increase what you can build.
Yeah. Yep. Security as well as scalability, which is
Yeah.
what we are, at least I'm of the understanding this is preventing a lot of applications at scale. But when we think of Web 2 applications, it's the user experience feel when you use it, the smoothness of it, but it's also the scale at which these applications can operate. And we had a podcast with the founder of Connext, a cross-chain messaging protocol, the other day, and he mentions these Web 2 monopolies, which he believes are going to be decentralized by Web 3 applications, but Web 3 is not at scale where it could support these decentralized applications.
Exactly.
And we've talked about security for most of this conversation, but there is also a benefit of throughput and scalability, which could bring about these Web 2 style applications at scale.
Exactly. And one of the ways we like to think about it is when we think of building Web3 stacks, you're trying to build things on top of each other that leverage the same trust assumptions as the underlying layer that they're built on, right? Because if you start adding weak points into the stack, it's very hard to build applications that have the requisite security required to really function in a decentralized world. Where ideally, if you have your base layer of Ethereum, you want all of the scalability solutions that settle on Ethereum to leverage the security of Ethereum. You want all the middleware that those applications to consume to leverage the security of Ethereum as well, or to be able to be, zero knowledge and leverage the security of wherever they settle. And so this is how we sort of think about scaling effectively and scaling securely, and making sure that as you build these applications on top of each other, you're able to build things that stay as anti-fragile as the simple applications, right? Because the reason we still use DEXs instead of, the order books is, I would argue, not because you can't build a crypto order book that is quasi on-chain. It's because if you're going to rely on something that's on-chain, you want to inherit the security that's from the chain. And if you want to rely on an off-chain order book, you're going to rely on an off-chain order book. As you think about building these more dynamic applications on-chain, like building a central order book on-chain, it has to leverage the underlying security of the chain for there to be a case for it settling on-chain.
And these chains have different security models. Like if you were to build this between Bitcoin and Ethereum, a central order book, how would you reconcile proof of work and proof of stake?
Exactly. I don't know how you would actually even build a central order book between those two. I'd imagine you'd want some kind of drive chain or some of the new Bitcoin constructions that I am not an expert on. But
okay. Well, I think those who are still with us are relatively technical. So I'm curious about Lagrange's influence on ZK proof constructions.
So we have a number of proprietary constructions that are very, very performant for our use cases. And the use cases that we are optimized for is very much this distributed computation on top of on-chain state data. I think you're maybe familiar with some of the sequential execution models for ZK VMs, right? That's kind of the risk zero, the nil foundation, as well as the ZKVM work. What we focus on is distributed computation. So things like Spark, Hadoop, RDD, distributed SQL, and some of these more parallelizable execution models that can now be run on top of large on-chain data sets in a zero-knowledge context, which we think is very viable when we start talking about these highly fragmented on-chain state layers and being able to synthesize all this data analysis on top of that.
Could you talk a little bit about how important SQL is to the non-blockchain applications now?
Yeah. So I would say distributed computation broadly is the dominant paradigm in Web 2 for processing large data sets. And there are different ways that can be run. And distributed SQL is one of those that's very viable, as well as things like MapReduce and RDB, which are ways to process large amounts of data in parallel execution formats that can scale with log. And what that enables is for you to run these very large computational jobs that are in parallel and highly efficient instead of sequential, which would then scale as the amount of data increases, right? Because if you had to run a giant loop, for example, right? If you're familiar with like loops in computer science, where you're just running through everything one by one, as you grow the amount of data, that loop gets longer and longer and longer and longer and longer to the point where it takes forever to run. You don't really want to run it anymore. Well, the question is, what if instead of running it all individually, you ran each loop instance one by one on a different machine and then merged them all together? You could, in theory, run that as a function of the time it takes to run one of them independently, and then the time, because you're doing them all in parallel, and the time it takes to merge. And so you can run these very large computational jobs, and SQL is one of the examples of what you can do with this very efficiently. And you can do very expressive computation at scale. And this is very common in Web 2 and very common in the big data stacks leveraged by most large Web 2 companies, right? Facebook, Google, Amazon all have huge data lakes and huge data engineering teams. What we do is we allow this type of analysis to be run from a DApp trustlessly on multi-chain fragmented state data.
And this is before it translates to Web3, these Web2 companies are still using AWS, Microsoft Azure, these cloud compute services to provide parallel computation.
Yeah, they do. They run that. You can generally spin up parallel computation jobs in all of those.
Okay.
But in Web 3, if you think about it, right? Let's say you're a DApp and you want to price something based on moving averages of multi-chain DEX states. So you want to determine where to allocate assets to from a yield aggregator by running a series of analyses on lending app performance across a few different chains. And then you want your DApp to be able to independently decision where to deploy assets to based on lending rates that are across 3 different chains. In that example, you would need to be able to process all of that data rapidly so that your lending app can analyze it and decision, or your yield ag can analyze it and decision. In that case, you need efficient computation and you need to be trustless in a zero knowledge context. And that's what you can do with this type of computational model.
Yeah, and it benefits. I think of it as these kind of 4 steps that you would need to go from chain to off-chain Oracle to then computation of the data in this Oracle database, and that's each step. Is it's just further away from the inherent security practices and the latency increases as you take more steps away from your ultimate destination, which would be taking it. Well, right now Web 2 goes to these clouds. The cloud pulls them down, so it's like one off from each of their internal data computation engines. But the security practices, if you just go directly, as well as the scalability, the security benefits and the scalability benefits are greatly increased from a direct communication between those chains or those Web 2 applications or those financial institutions, or the integrity of that data. and the scalability of that data. And I, I'm I see like the inherent security benefits,
Yeah,
the scalability benefits, um, and I really enjoy the idea of scalability benefits. I think security is like
yeah,
so important, but it's boring.
yeah,
Sorry, but
yeah,
like scalability is so exciting because we can think about all the possibilities of what we can do with more technology, more
yeah.
just more real estate, to kind of think about these applications that are now possible with this innovation. Um, and you combine that with kind of the idea of the nested rollups. It doesn't just have to be ZK.
Yeah.
We can increase scalability by nesting these rollups, nest Arbitrum and an Optimism. Ethereum sharding could just be a series
Mhm,
of nested shards. So the opportunities like to innovate further in scalability are
mhm.
greatly unleashed with a direct channel to share the state of chains. um was this a Lagrange theorem? Like which
No,
theorem is this that kind of like opened this whole field up?
so I think the way we see settlement layers is that and execution layers is that we're increasing the amount of block space, but we're not increasing the amount of tools that allow you to interop between block space. In other words, you're going to have thousands of app rollups, likely in the next few years with all these new app rollup as a service providers that are launching. You're going to have L3s on Starknet, L3s on ZK Sync. You're going to have Orbit
Yeah.
rollups on Arbitrum. You're going to have OPT stack chains. You're going to have all of the or OPT stack rollups. You're going to have all these different rollups that are being created that are all settling on different settlement layers and all have their own independent execution states. And so what you need to do is to have cross-chain models that can properly interact with all of this different state safely. And when I say safely and security, like I agree with you that in the purest form, security can be very boring. What I think security and scalability, where they become interesting, is when you think about what you can build on top of them. Like think about just a very simple yield aggregator, like a Urine or a Beefy, right? Well, how does it allocate assets? Every so often, there's a tend or a harvest function call, at which point these yield aggregators rebalance and allocate assets across a series of different yield-bearing strategies. These function calls are called whenever someone deposits assets or whenever there's a regular interval that passes. And they're constrained by only being able to access the data that they can directly read, right? And now you talk about all these different applications deployed in all these different chains. Are we going to have thousands and thousands of independent yield aggregators? At some point, it doesn't make sense. What you need is to be able to have yield aggregators that can compare multi-chain state with the exact security mechanisms they use today to be able to now take a single chain yield aggregator and make it capable of deploying assets multi-chain. That's the kind of things that we think this type of technology very naturally unlocks. To take a DeFi app and then to expand what you can do with it.
Yeah. Wow. This is heavy, and I expect that there's like you know, this is going to seem so obvious to people like in the long
Mhm.
run, but then it's going to people, just developers are going to have that moment like why didn't I think of that? Um I think it's what we all think of, as like an idealistic interconnected um blockchain,
Mhm.
which is also multi-chain with like kind of a diversity built into it for
Yeah,
uniqueness, competitiveness, and choice, where you can still choose to operate um, on one chain or another. An app chain,
yeah,
Axie Infinity, the NFT game, has its own chain.
exactly.
Layer threes and fours and five ultimately are app chains depending on how many applications are deployed on that
Yeah.
particular chain, and the interconnectedness of all of those applications, um, I think was
Mhm.
a aspiration to a lot of developers and
Yeah.
has not been executed on yet until now.
I think we're at the precipice of some very exciting innovations in scalability, security, and cross-chain functionalities. And I think to your point, it's going to unlock a lot of new application layer products that we're going to really be very excited about. Like I think Blur is one that we're very excited about as well. I think with what we've seen with the Blur airdrop, smart tokenomics and distribution strategies can really drive interesting adoption patterns. And as you now start thinking about being able to process large amounts of data, you can start building things like Blur that are not decisioning off chain, but are in fact decisioning on chain, like autonomous, trustless airdrop mechanisms, like what Blur runs. And so what you can create is some very, very exciting applications that were otherwise infeasible before.
Yeah. The classes of applications out there are so, I mean, they're endless, right?
Yeah,
Like, which is really, really cool to like let your imagination run about what you could build with just frankly way better security, way better scalability.
exactly.
There's all the new primitives,
Yeah,
spoons, if you will, whereas you could fork a traditional finance institution, architecture, all of the
exactly.
Web2 applications that people know and love, you know, to call them forks is maybe a little bit
Hmm.
disrespectful, but like people like using these applications, they spend time on them,
Yeah.
build relationships on them. Um, could could pragmatically choose an architecture of a distributed compute, um, and provide a better product, arguably, at kind of just the behind the scenes, under the hood components that
Mhm.
aren't really facing a user experience, and the majority of users would not notice,
Yeah.
except for the increased performance.
Yeah. I think that's very exciting, and I think we're very close to converging to a point like that. With the growth of ZKVMs, with the growth of scalability solutions, and the growth of tooling for interoperability, like some of the stuff that we're building, I really think that it's going to be this kind of aha unlock moment for a lot of developers who can now build things in Web3 that they couldn't build in Web3 6 months ago. Where 6 months ago you were constrained to very small function sizes on Ethereum with very limited data access, no historical data, no real trustless cross-chain data, static price feeds with complicated and opaque risk assumptions associated with them. And now you'll be able to access data from anywhere. You'll be able to access derivatives and analysis of data from anywhere, and you'll be able to build far larger and more expressive applications that are more secure, more fault tolerant, anti-fragile, and are actually a lot more fun for the end user to play with.
Yeah, right. Yep. And that's what like the majority of users are looking at is like how much fun it is. But
Exactly.
then uh, yeah, that's great.
Exactly.
For mass adoption and
Yeah.
all these types of applications. Um, this has been a blast. I know we're closing in on time.
Hmm.
I'm still curious which Lagrange theorems impacted the construction of not necessarily Lagrange
Yeah.
innovations in particular, but just like um, what kind of mathematical theories did you incorporate when thinking about ZK proofs,
Yeah. So
and anything
twofold.
else you'd like to share?
Yeah. So twofold. Lagrange interpolation is a component of zero knowledge proofs. And it's a component of a lot of things in mathematics and cryptography. Also, we love the kind of the mental model of the Lagrange point, right? This point in space between two large celestial bodies where an object sitting there rotates on its axis instead of being drawn to either of the large massive bodies, because it sits at a point of equilibrium between the gravity of these two large objects. And I'm not a physicist, so I might have butchered that explanation, but that's roughly speaking what it is. And we've loved that concept
This is the
with
Lagrange point at the
yeah,
middle of these other two celestial bodies, or
exactly.
caught up in
And
their magnetic fields. It's somewhere
exactly. Instead of
around
being
them.
drawn towards either, it sits in the middle and rotates on its axis.
Okay.
And we've loved that concept for
Oh,
cross-chain because we think of these chains as these two massive settlement layers with huge collateral on the validator sets, huge security, huge communities. And cross-chain, in our view, should fundamentally be this very light piece that's drawn towards neither, that doesn't have any influence or effect from either, and just sits there, exists in the background, and allows for things to happen.
like a revolving door, just chain and Just kind of you're just passing through. Cool. And okay, so that's the Lagrange point. And anything else you'd like to share about your build process so far or your
Yeah,
journey kind of up until this point?
we're very excited about having a testnet launch that's going to be this summer for our Lagrange point, our Lagrange state proof infrastructure, which we'll be integrating with some very early development partners that we're excited to announce soon. And then we're also intending to have a test net for our first ZK big data product, ZK MapReduce, likely later this summer as well. And I think these are going to hopefully be aha moments for a lot of DeFi developers, kind of seeing what they can interact with and seeing what they can build with these new paradigms. Our cryptography team has been hard at work, and yeah, we've been pushing forward some pretty big advancements recently. We've been actively growing it pretty quickly. So shout out to everybody on the Lagrange team.
Cheers, guys. Yes, really excited to see the product of the research and the thought
Mhm.
you guys have put into this. Where can people find you? If listeners want to reach out, maybe they work
Yeah.
with a project that are interested in integrating.
Yep.
How could they contact you?
So our website is lagrange.dev. And our Twitter is Lagrange Dev one word, or at Lagrange Dev one word. You can contact me. We probably easiest on Twitter, at Ismail_H_R, or you can email me, which I probably shouldn't say my email, but it's ismail@lagrange.dev. It probably wouldn't be very hard for anyone to guess.
Cool. Awesome. Well, it was a pleasure having you on. There's one last question that we ask each
Yeah,
podcast guest. If you the analogy we use or hypothetical is if you're stuck in an elevator, which is,
yeah,
let's say you have an elevator pitch, 2 minutes to explain to anyone. You could explain, anyone dead or alive, Lagrange, what you guys are building, and ZK's
yeah.
technology, and who would you choose and why?
I would ideally talk to Web 2 data infrastructure and data engineering developers, and I would explain to them the types of dApps that they could now build in Web 3 and how they leverage very similar computational models and can be built with very similar computational models to what they can build in Web 2. I think when we unlock this larger pool of developers who are focused on some very specific aspects of the application stack, we're able to build things that are far more robust and fault tolerant. I think as the number of Web3 developers can start to become this pool of Web2 developers too, we're going to be able to have some very interesting things built that are far more secure and far more fun to play with. I think there's a lot of great developers in the world who've been kind of turned off from Web3 development because of how kind of niche and specific a lot of the engineering paradigms are. And as we start opening up and expanding the engineering paradigms to be closer aligned with what you could build and how you could build it in Web 2, you're going to be able to have a larger pool of people who are building applications that settle on chain without having to understand the semantics of how the chains work. I
Got
think a
it.
good application, I think a good infrastructure developer now asks themselves, how can I take this incredibly complicated, dynamic, and insider focused and insider specific domain expertise that someone would require to hold in order to build something in Web3, and how can I synthesize all this into a simple product that a developer who understands the engineering frameworks but doesn't understand where the engineering frameworks are being applied can now leverage it.
Yeah, this goes out to all the massive Web2 monopolies.
Mhm.
Bezos, Zuckerberg, if you're listening, it's Ishmael_H on Twitter. Reach out to him. And
Say less of those guys and more the developers who are working at those companies and who are interested in starting to leverage some of the cool innovations that they've had in their application level development on Web3 with this type of application level development.
yeah, yeah, yeah. You guys, everyone, reach out. Ishmael on Twitter, and it was a pleasure having you on. Yeah,
Thank you,
I
Rob.
hope we stretch this far and wide and share Lagrange with the world.
Thank you, Rob. Really enjoyed being on.
Likewise. Cheers.
Cheers.